Okay, good evening, good afternoon, everyone. So let's begin with the in-person physics talks with this. It's usually going to be at 3 p.m., but today was an exception. Otherwise, it'll be 1 hour or so after lunch. So you have enough time to climb up and also for the speakers. Okay, so as you know, just before we actually begin the talk, how these things have been arranged. In week 0, we had a bunch of talks which were slowly building up. Some of them were more basic and they were slightly climbing up. Now in this week 1 and week 2, we want to expose you to research level topics. So these are not intended to be pedagogical talks. They are intended to be more as an exposition of the various research topics that may either be relevant for the Wolfram Physics Project or that may be something that someone in our team cares about, and it may also be topical. So half of the speakers are from outside, meaning they are professors in various universities doing cutting edge research. So you'll get an exposure to that, what's going on, and also what we do. Since these talks are advanced and they are 2 hours, what I think you should keep in mind is that it may not be possible to define each and everything, but I hope to give an intuition of the main things that are relevant. There may be certain things I tell you without defining it in complete detail because there may not be time, but I'll give you the intuition and then you can look it up later. So that's how it'll go. The most important thing, including in this talk here, will be to get a sense of how these ideas connect. That would be the main thing you should try to take. Feel free to interrupt me. Also, those of you who are on Zoom, just interrupt me. I'm not checking the chat. I cannot multitask that many things. So just speak up if you want to ask something, and your audio, if it's clear, I'll hear you. Okay. Good. So that being said, if there are this talk, what will it be about? Let me actually first tell you how these things are. All the speakers who are going to speak this week are more or less telling you about their research, including me. So whatever I say is up to me. I'm not, I take full responsibility, disclaimer, whatever you want to call it. I'm going to tell you about what my opinions are or what my views are on these things. Different people in our team, in a healthy way, have different views. So I'll point that out. But these are my views. I'm not repeating somebody's paradigm or somebody's thing. I'm interested in many things, but I'm going to tell you what exactly this is. And the other point is that many of the talks you have heard so far have been computational talks. I am less interested in the computational side, meaning the computation as a methodology. I am more interested in computation as foundations. And for that, most of the time, I have to resort to a mathematical conceptualization of the topic. And that's what I'll be talking about. That is what I like. And that's why I am also somehow at the Wolfram Institute to do those things. I'm interested in the math side. So if I have to make a controversial claim, I would say a mathematical understanding of these things is way more important than everything else. But again, as I said, that's my opinion. Now, in order to just set the stage of, you've been hearing many different things and you will. So I want to show you a way to place the pieces together. And this will be in the context of the Wolfram Physics Project as well. Now, generally speaking, the Wolfram Physics Project is about fundamental physics. It is attempting to explore various puzzles and questions at the foundations of physics, and by extension, even mathematics and computer science, because its inspiration comes from all these three things. It's not coming from pure traditional theoretical physics or traditional mathematics or traditional computer science, but over the years, these intersections have grown, and other people have also recognized it's not some outlier, crazy kind of thing. There are reasons why various researchers, academicians work around this. But just to tell you how to, in your mind, kind of compartmentalize the various approaches to these things. So, typically, if you have any scientific phenomena, the two kind of major branches would be experiment and theory. Let's forget about experiment for now. That again, I'll be less interested in. So if we just talk about theory, theory, you could say broadly, you can study it on two sides. On one side, there's the mathematical study of it. And the other side, there is a more computational study of it. Now, traditionally, the mathematical thing itself would break into two branches. One branch would be, let's say, phenomenological models. And the other side would be, let's say, what you would typically call mathematical physics, or you would call mathematical foundations. And on the computational side, there would also be actually two branches. One would be more trying to play with simulations. And the other actually would be emulations, which you may not have typically heard from traditional physics kind of, let's say, expositions, but in engineering, for example, if you go sit for some theoretical engineering class, you'll see a lot of the times, sometimes they may be just simulating certain problems, and you can simulate when you have things like equations of motion. But sometimes you may resort to emulations. And I'll say in a minute what that is. So these phenomenological models would consist, for example, equations of motion, dynamics, differential equations, the typical thing you have when you do textbook physics. And once you have these, I'm calling them phenomenological models, but I mean, basically I'm talking about equations of motion, dynamics, and think of them as phenomenological because the variables and the evolution rules exactly directly refer to phenomenology, direct observables of what they are. And when you have this, these two things connect. You can have this differential equation of analytic solutions, and then you can simulate them, and you can have these simulations. Now, when you don't have the possibility of deriving some partial differential equation, or for whatever reason, you're not able to make a model that is directly connecting to the world, or even if you do that, like the case of quantum mechanics or something, you may have Schrodinger's equation and all that. But Schrodinger's equation doesn't tell you everything about quantum theory. People always say, oh, but what about the foundations? What does it mean? What are these objects? What is the wave function? What is the philosophical ontology? What's the conceptualization? So all that part comes under so-called foundations or mathematical foundations. And these are usually described in a kind of abstract conceptualization. These things can sometimes be part of what you could otherwise call metaphysics. Metaphysics, not just as some kind of philosophical babble, but metaphysics in a more kind of mathematical sense. And when I say abstract conceptualization, I mean a mathematical formalization, not just not like just giving some kind of statements. Like there are many branches of philosophy. Here I would resort more to the analytic philosophy as opposed to the others. This is not just about talking about some observations or just making some axioms or assumptions. Mathematical foundations of any field, including quantum theory, or even like classical systems, one may seek the foundations, but there it's not so complicated. So that has to be described in some mathematical conceptualization, some mathematical formalism. That formalism hopefully is something that underlies these equations of motion. Even if you have the Schrodinger equation, there's more to understand about quantum theory, and that understanding should come from this side, and it has to be formulated in some abstract, depending on exactly what's the problem, it has to be formulated in some abstract sense. Here, what we're going to talk about in this talk is largely going to deal with pregeometry. So in pregeometry, we are talking about geometry itself is necessary to understand gravity, and if you want to go further, quantum gravity. And there are models of quantum gravity. There are lots of approaches, lots of research going on, lots of effort and money and manpower and going into various. There are many theories of quantum gravity. Let's call it approaches rather than theories because they are still under development. But you may ask that behind all these approaches, is there some foundation? How should we understand geometry in a fundamental way? And for that, to understand something, the lesson that we have learned in various kind of things like this is that to learn something, you can't just be dealing with looking at that thing itself. You have to look one layer below. And that's why pregeometry is a term that's going to be used for conceptualizing the building blocks of geometry itself. What exactly that means, I have to tell you, and that's the kind of thing we'll discuss. But that has to come, that sits on this side, and that has to be done with some kind of formalization. And here in this talk, I'm hoping to give you some glimpse of the kind of mathematical formalization that can give us some clues into formulating various, let's say, meta theories or sub theories of pre-geometry. The goal of this approach would be that if one has such an understanding of geometry, then one may be able to bridge all these different approaches to quantum gravity and maybe understand geometry itself more fundamentally. Not that this is then going to be some new theory or something, but it's going to explain something underneath what's given, as opposed to current approaches at this level. When you do more phenomenological model building, you say, let there be this structure, let there be that, let there be this, and now you write your differential equation. So instead of all those, let there be this, this, and that, here we are trying to ask, what exactly can you let there be? How exactly do you formalize your theory? What should be there in the axioms, what should not be, so on. That's the whole heart of mathematical foundations. Now, in computational, in the computational approach, when you don't exactly have these kind of things, like these differential equations and equations of motion and so on, sometimes you may not, because as you know from your own experience in physics and mathematics, there are lots of systems that are not exactly analytic. And in computer science, one may recognize that there are systems that are problems that are non-computable, or as Stephen would call, computationally irreducible. So for those kind of things, you may not be able to do these kind of straightforward simulations. But what you may do is, if you have some idea about the abstract conceptualization, you may still be able to build abstract models, which are not exactly equations of motion or predictive models of the kind that you'd then see in an experiment, but you may be able to build slightly more abstract models that can be used for emulations. So suppose someone tells you that, okay, in this particular theory, this abstract conception comes from, let's say, for simplicity here, rewriting rules, but it could be something else. Your formalization may not be based on rewriting. It may be based on some other kind of axiomatization, and you have certain atomic structures as the building blocks of that framework. In this case, for simplicity of example and for familiarity with you, let's say we say the rewriting rules and the rewriting procedure is this abstract building blocks. Exactly how that happens, I have to tell you. You can't just, that's not just a priori obvious that it should be, or it should not just be taken in this way. It has to be seen in a very specific form. But suppose, for the sake of discussion, the rewriting objects were the kind of basic things, basic building blocks of some kind of thing, let's say of geometry. Then one may work with those and try to ask that within this mathematical formalism, what type of calculus can that system admit? Or in other words, what kind of logic can it permit? And according to that, what kind of compositions or what kind of calculi or logical structures, etc., can you combine and build those things? And from that combination, you may say that instead of simulating, you're just emulating some behavior based on these things. In many ways, what you have seen up to now, especially in Stephen's presentations and other things, he may not have kind of put it this way because he's not really interested in the math side of things. His intuition and motivation comes more from the computer science side. What he's actually doing is this side. He's taking as a kind of starting point that this rewriting structure is the basic building blocks. And then you may wonder, what does that mean? Is it ontological? Is it just representational? What is it? All those things have not been clarified. But he's taking somewhere that, okay, my atomic elements, atomic structure are these rewriting these rewriting systems, whatever they may mean in an abstract sense. And then they have certain rules, and when you just let these rules do their thing, you emulate the system. You're not simulating it, you're emulating it. You're putting a representation of what you believe may be the building blocks, and based on those representations, you're letting the system do its dynamics or so on. And one is making some kind of inferences. So in a way, if one does not have this mathematical foundation and all that, this emulation, if you just do it like this, it will look loose. It will look like, where did this come from? You could just take anything else. Why take a rewriting system? Take ones and zeros, and like people have historically done, just take binary bits and find some weird ways of combining ones and zeros, not just in a line, but let's say in three-dimensional space, and like in all the movies, you have cubes of ones and zeros. You could just do that. So without the mathematical foundation, this side may look weak. So one of my main interests is to provide a mathematical formalization to what we do in the Wolfram Physics Project in terms of the rewriting systems. It is not so much the real kind of motivation for me is not whether the Wolfram Physics Project turns out to be a theory of true theory or false theory or fundamental theory or not fundamental theory. Given that those are the assumptions, I want to ask, how can we understand mathematical? And along the way, we may even be able to understand that, well, when you look more carefully at this kind of formalization, one may be able to, realize that, okay, perhaps the way we were thinking about it is not exactly that way. One has to be a little more careful, make little more subcases, make it more and more specific or specialized. So that's the benefit of really whatever kind of ideas are there, whatever kind of approaches are there, etc. Understanding and working on this side gives a much better handle on this. It doesn't mean that by doing this, one will directly be able to make phenomenological models straight away. As you see from the lesson in quantum theory itself, many times people first discover things here and then they find this, or then they dig into this, because from these abstract foundations, there are many ways you can go. But anyway, now that we are working with these kind of computational approach, it is worth asking what this means, and that's what we are trying to do. So that's what we try to cover in this talk. And as I was saying over here, emulations is not so uncommon if you look outside typical physics curricula. In engineering, a lot of the times people actually they try to build so-called observer models, or kind of they mimic the dynamics of a system in something else. A very simple example is this, though this is not exactly what neural networks are used for in the AI community. But for example, if you look at a neuroscientist or let's say a control engineer, what they do is when they want to control the dynamics of a system, let's call that system the plant, as it is typically called, you emulate the dynamics of that in some other system, which is completely different. So this thing could be some complex mechanical system based on wheels and gears, and that thing could just be a network with some weights adjusted, or it could just be some equations with some parameters that look like some learning rules. And then based on that, you can mimic it. And in a way, in many ways, you can imagine the way our brains, the neural networks of our brains, build models of the world is like that. They kind of they map the entire representation of the dynamics of whatever system or the world model that is studying, and they code it in its weights and build an internal model of that. So these internal models and the running of the internal models is what one can do by doing this. Of course, you may even work at this level when you have the luxury of doing that. But sometimes you may not have the luxury, or this side of things may not be analytic enough. And as you see from these lessons in computational irreducibility and non-computable problems, etc., sometimes you don't have a predictive equation whose solution will tell you that this is what the system will do. And in those times, you have to ask if there are other ways in which you may build a representation of the system and let it do its thing, and then see what it has done, and then study its behavior. So that's where these kind of things are important. But here we focus on this, and this is where everything can connect together. Okay, so that being said, let me first just thank a few people who have been working with Hatem, who is one of the remote mentors here, and Dean Rickles, professor in Australia. And most of these talks will be based on these papers. They are all of them are somewhere in the reading list. You can, for further details, go into these things depending on what kind of what subtopic has been of interest to you. And let's get started then with the bulk of the material. So what we are going to do over here, we are interested in, we are really, the core of this talk and the part 2 of this will be about pregeometry. As I mentioned, studying pregeometry is of direct motivation for understanding the underlying foundations of any quantum gravitational approach, because it is trying to understand what geometry itself is. Classical quantum, doesn't matter which one. What are the building blocks of geometry? Now, before I try to just answer it in our way or some things that we have stumbled upon, it is useful to just see where these ideas come from. These things haven't just come out of the blue. All this is built on a tower of work that has been done since decades. Of course, I mean, depending on what department you are on or what school of thought you come from, you may have heard one approach over the other, like, the typical fights. If you're in a string theory group, that is the holy thing. If you're in a loop quantum gravity group, that's the holy thing. They don't bother at all to learn anything of what anyone else is doing. Kind of that approach is sort of no more useful because things are getting more complicated. And it's necessary then to just kind of take in all the different things that are there and synthesize ideas and see what we can do with it. So what we care about is, we want to ask, when we talk about pregeometry, we think of pregeometry here as the building blocks of geometry and spatial structure itself for any approach to quantum theory. Let's say in this case quantum gravity, but when you think about quantum gravity, then it would also mean any approach to field theories that are existing on that kind of geometry. So in a way, if one has to stretch it, one should think about these building blocks for everything related to space-time as well as fields. But just to keep things a little bit grounded, I'll focus more on the space-time part, and I'll just point you to references where people may also be thinking about this in terms of trying to see how field theories may look on discrete backgrounds. As you know, that traditional quantum field theories, which is highly successful theory, is all formulated on continuous geometries. And it's a big challenging task to start thinking about what a quantum field even means on a background that is not continuous. And how should one write down the axioms of field theory? What would it be like? Those are important problems. And not only that, but you may have heard, or perhaps you will, that field theory as we know it, while it is extremely rich and one of the most successful theories so far, it is not even the end of the story. Over the years, people have realized that depending on what kind of specific cases you look at, or depending on what kind of special geometries and very kind of exotic parts of the universe you look at, there are more kinds of field theories than we have still discovered. And those may be what sometimes people refer to as higher field theories or higher gauge theories. And that term higher will also be relevant to what we talk about. In this case, when we say higher, it will directly refer to some higher mathematical structures. So I'll point you to what those structures are. So as such, we want these things as building blocks of geometry. Historically, this kind of things were thought of by John Wheeler. Now, John Wheeler is extremely well-known, famous physicist. He's not alive anymore, of course. But for any of you who start doing your first course on general relativity, the first book or the Bibles is the Misnathon-Wheeler book, the big fat one, called Gravitation. And Wheeler is one of the authors. But besides that, Wheeler was an extremely influential physicist back in the day. And not only was he in the beginning, of course, he did lots of important contributions to physics, but towards the latter part of his life, he went deeper and deeper into these conceptual problems, including pregeometry, including what the role of the observer in physics may be, and all those things he has written a lot about. So Wheeler, in some sense, will be a bit of a starting point and an inspiration for these things. He's the one who originally coined this term pregeometry. And for Wheeler, there were certain kind of motivations for why one should think about this. So one of the things for Wheeler was that he said that, look, the universe can expand and can collapse. So let's say that, suppose the universe collapses and we think of the universe as space-time and matter. Then what is left? If something is left, it hasn't collapsed. And if it has collapsed, nothing should be left. So what is there after it has collapsed or before it has emerged from some Big Bang? Irrespective of whether one cares about the Big Bang or not, aside from that question, at a conceptual level, what the problem he's posing is, if it collapses, or if it just comes from nothing, what is there? There has to be something that transcends space, time, and matter. And that transcendental thing is what he was kind of thinking of as some sort of pregeometry, something that transcends space, time, and matter. In other words, this means that if we want to think about what should be pre to geometry, it should not be geometric itself. You cannot say that the foundations or the building blocks of that thing are that thing itself. It has to be something beneath it. Of course, that also gives other problems. If it's something beneath it, you can ask what's beneath that, and that, and that, and that. And that's the famous infinite regress problem in philosophy. If you look at philosophy of epistemology or other things, you have the so-called infinite regress problem, which is more like, in simple words, it's like saying that if you think that there's something that's fundamental, and if it is some interesting structure, some physical structure, let's say, it could be whatever, then you may say, okay, but what builds that? And then you can go on that way, and that will be the infinite regress problem. So how does one address that? So even if one has the building blocks, one may land up in such a situation. But anyway, so just to give a heads up, what we kind of point out here is that whatever this pregeometry is, it cannot be physical. It should be something that is pre-physical. Physical means what? What do I mean by physical? Space, time, matter. That's what I call physical here. So this cannot be any of that. So it cannot be physical. It has to be something else. What else can one even imagine? So Wheeler had some suggestions. Besides Wheeler, way back, for those of you who know about Leibniz and his monadology, Leibniz had certain thoughts which actually inspired Wheeler. Leibniz wasn't thinking of physics the way we talk about, but Leibniz was thinking of philosophy and metaphysics. And when in that day, when people used to think of metaphysics, they are really thinking about the nature of reality very generally. The term reality is a little bit vague. So as a physicist, we wouldn't use that term now. But metaphysics isn't about the vague part of it. Metaphysics is really about the foundations of physics itself, in the same way like metamath is about the foundations of math. And Leibniz's monads had some of that flavor. His monads, Leibniz, of course, was thinking about not just about geometry, but more general things. He was saying that something should be there which is not necessarily material, nor it may be mental. He was thinking about it in philosophical terms, what people may call as some kind of monist substrate. And there are still approaches to some kind of monism that people study in respect to, let's say, the mind-matter problem. That's another story. But Leibniz had these kind of ideas that something has to be there of some sort, and that thing isn't just a thing. Importantly, it has to have some rules of composition, like a calculus. And based on that calculus, it should be able to compose structures. Almost like, I'm not saying it's the same, but almost like saying that you have some cellular automata and there are some rules and then you build structures, or you have some rewriting system and you have rules and build some structure. So the recurring story is that whatever these things are, people have been thinking of, they should be rules with which you should be able to compose and build structures. But if there's something and there are rules to build structures, that cannot just be any wild system. One has to still make a difference. One still needs something more specific. And that more specific sometimes comes from the, so, you know, as we've often been saying, in physics, there's this kind of thing that, at the fundamentals, things should not be continuous, they should be discrete. It's a lesson that we kind of inherited from the early days of quantum theory. So it's not just enough to just say that, well, there may be some structure and you have some rules of composition. Discreteness should play a role in a fundamental way and so on. And of course, Wheeler also had that kind of thinking because at that point, you know, at the 70s, he was involved, or he was directly at the front seat of all those kind of ideas in theoretical physics. So even Wheeler was thinking that, look, I mean, this thing about quantization is an artificial thing. We take a system, we write it down, we take a theory, we write it down classically, and then we quantize it. But how does nature construct itself? And why is he even saying that? Why is he saying nature construct itself, as if nature is a thing or something, or a being or something? One of the motivations is that when people in those days, and even now, when they think of the problem of quantum gravity at the level of the universe, you can't assume that there's something outside. If it's a closed system, that is the system itself. If you are outside, then you could say, well, I'm looking at it from the outside, and perhaps there may be things that someone from outside may influence it or so on. But the view from the inside means everything is closed. The system has to take care of its own. There's no help, so to say. It has to do its own thing and build itself. How does it do it? There's no programmer outside, so to say, if it's a closed system. So how does the system have this information? In a way, you can say, oh, come on, we've seen so many closed systems. It's not exactly the right analog, but I'm just trying to tell you that if you think of biology, and let's say you have a fetus or something, all the information is there in the DNA. Of course, it's not completely closed because it still needs various outputs, external outputs, and so on. But there is information packaged inside, in some sense. So you're also the kind of question you can ask: this really completely closed system, which is the universe at a quantum gravitational level or so on, how exactly is all the information packaged itself such that it can do its own thing? In a way, so Wheeler was thinking, what are the methods and materials that nature herself uses to build the world? You cannot just be building the world classically and then quantizing it. That's what we do. What does nature do? And in that sense, Wheeler's approach was fundamentally constructivist. And of course, in this kind of way of thinking, like I said, Wheeler wanted to think about something that in which gravity and quantum mechanics merge at that level. And for him, he said he was kind of convinced that there has to be something underneath space and time. And one of the first suggestions that Wheeler had was that maybe, the only thing he thought that if I think of something that's neither physical nor mental nor material, so on, what can it be? It can just be something mathematical. It can be like propositions, calculus, abstract propositions. So he was thinking of logic, almost, that logic is the abstract thing. And from that, everything comes. Of course, he didn't have all the tools and the machinery, and that's not a complete answer, but that was his starting point. And that's a good starting point, not because it is the complete answer, but this is trying to say that we'll go in a direction where we try to think of these building blocks from some abstract mathematical system that is fundamentally having some logical underpinnings. And now, unlike then, there are actually advances in that mathematicians have made. And mathematicians are not like intrinsically interested in physical problems per se. But what's interesting is the following observation that, mathematicians have spent decades and years, and maybe more than 100 years or so, trying to build the foundations of math. First, they were looking at set theory as the basis. Then they realized there are some paradoxes. Then they started looking at category theory. Category theory was fine, but there were still some further problems and specifications that needed. And then they started looking at so-called type theory and homotopy type theory and so on. And those efforts are as recent as maybe 10, 15 years or so, the latest part of that. And there they are kind of trying to ask whether, these very philosophical questions, is math constructivist, or is it classical in the Platonic sense? Does it just exist? Or when we prove a theorem, should the theorem be constructivist or not? You'll see what I mean by that. But the machinery that they have built for answering those questions, incidentally and interestingly, that kind of thing comes in the realm of meta-mathematics. That same kind of thing seems to be exactly the kind of things we need for what we could call as metaphysics, or the foundations of physics. Seems to be like the same kind of tools are useful. Maybe more is needed, but apparently the same kind of things are seem to be useful. And we'll try to look a little bit into that. So one of the things I have to just add before, so here I will want to tell you about, so Wheeler was in the 70s. Several things happened then. Then more kind of moving on a little bit ahead, when more machinery and more formalisms were developed, sometime around let's say the late 2000s or 2007, 8, people like Chris Isham and Andreas Doring started thinking about this problem. Now, those of you who do come from a theoretical physics background, you may have heard of Chris Isham. He's now a senior retired professor. But Isham was at, not all, but many or most of the current approaches to quantum gravity that exist now, and all the front runners of that, they were all students of Isham. He was among the, at that time, at that time of history, for whatever sociological reasons, quantum gravity was not exactly a cool thing. It was looked upon like something that is a little too wacky to deal with, because we don't know how to talk about the problem, we don't have the machinery and so on. And Isham and some of his collaborators were the first people to say, no, we should take this problem seriously. We should try these approaches. And several of his students are now at the like the leading front runners in various of these theories. So in a way, a lot of people thank him as the father of the modern quantum gravity in some sense. And at that time, Andreas Doring, who was a postdoc of Isham, they worked on an approach where they were thinking about saying that let's forget about a specific problem right now. Our main goal is that instead of working up into a specific theory, we need to build a mathematical framework, typically in the sense of these foundations, which can encapsulate various types of existing theories, and from which one can even get more theories which have not yet been considered. So instead of working with a theory, they wanted a formalism which is like a meta theory, literally a foundation from which all kinds of approaches to physical theories should happen. So, for instance, in this kind of framework, one should be able to say that, okay, in this framework, if you look at this type of structures, then you get classical mechanics. If you look at that type of structures, you get quantum theory. If you look at that kind of structures, you'll probably get quantum gravity and cosmology. And maybe there'll be in this meta space, you may be able to find pockets where theories that we may not have physically discovered because either we are not in the regime or so on, or maybe those are not something that those require special preparation of those states, etc. They may also be available. So they were looking really for some abstract structural framework within which all these things can be. And one of the main kind of things, assumptions they said is that in this kind of structural framework, if it has to be so general, right from the beginning, physical observables cannot necessarily be continuous. You cannot just assume that so what this means is that the starting point of that structure cannot be a priori continuous. They said we have to fundamentally start with discrete. Then there may be ways in which the discrete might coalesce and continuous might emerge. But fundamentally, you have to start with discrete. So they set about this program in doing this, and what they came up with is a so-called topos theory or topos theoretic framework. Now, topos is a part of category theory. I'll have to tell you what a topos is, and before that, I'll probably have to tell you what a category is. So I'll give you a little bit of a intuition and intro on those things. They came up with this approach, and in this approach, they stumbled upon the fact that in these toposes, in these mathematical structures called toposes, these are abstract formalisms that people have used again for the foundations of math. But within this, there is a inbuilt formal system which can, in effect, express some kind of logic within itself. And that formal system is, you can more generally call it a formal language, but I'll actually define what a formal language is as we go. But this formal system within these mathematical structures can express some kind of logic. And the kind of logic they express is not classical logic, but what is called intuitionistic logic. And intuitionistic logic is directly related to what is called constructive mathematics. Now, they came about this from this approach. So, in some of the well-known papers, they even asked this question: what is a thing fundamentally? Before I tell you about toposes, and here they were inspired by this thing about taking discreteness seriously and so on, and they came about with this. They did not necessarily start with Wheeler's kind of specific idea of just starting with a calculus or a logic, but they arrived at it by just being inspired very generally and looking at the more modern mathematics that was available to them. Now, in a way, just to kind of point, you may ask that here we are talking about the building blocks in this case of geometry, or it could be anything for that matter. Now, when you have building blocks, it is natural to ask whether they should exist or how they could exist itself, because there may be problems in assuming that building blocks exist. So there's that. In some sense, because of that problem, these building blocks, for reasons already argued by some of these previous people, they cannot necessarily be they cannot necessarily be physical. They have to be something pre-physical. So in many ways, one is asking about mathematical structures which don't have that much structure to start with. And sometimes, if you have heard Stephen use this term structureless structure, this is my interpretation of what he means, or this is how I interpret it within the context of this framework. He means it the same way, but his intuition for this comes from the computational side. I'm trying to now connect that term structureless structure in the context of what we can think about it from these pre-physical systems. So now if these structureless structures are pre-physical and a priori they are not continuous, they have to be discrete, then one may say, okay, fine. So it's all about discreteness. But you can ask yourself a little bit more. What exactly does it mean that everything has to be discrete? What is so special about discrete apart from the fact that it's not about continuum? It's not just about discrete for the sake of discreteness. What it actually, in a sense, for a moment, shift your perspective, and rather than focusing too much on discrete versus continuum as the main thing that you have to fight between, slightly translate your thoughts into some analog of it. Think about the dichotomy between the finite and the infinite. This is not the same thing, but conceptually, there's a reason to translate this. The issue so much is not about whether it may be discrete or continuous, but whether it's finite or infinite. And in a way, of course, if you come from pure math background, you'll say, sure, that's obvious, isn't it? If you look at examples like the Cantor set or other things, it's all about finite versus infinite. And from the physics side, because we focus so much on kind of discrete versus continuous, we sometimes almost pay less attention to the fact that really we are talking about finite versus infinite. And if that's the case, then the obvious question is, what is a fundamental theory of finite structures? Is there such a thing? What should this theory be? How should it look like? So if there was some kind of fundamental theory of finite structures, what would it do? It would have some atoms, some finite set of building blocks, or atoms, let's just call it atoms, and it would give you the rules of composition. And then from that, it would build various processes. Because it's a theory of fundamentally discrete finite things, it would only build finite or discrete processes. So the question you can ask is, what exactly is such a theory of finite processes? There may be many answers, but one particular answer that is relevant to us is, this is nothing but the theory of computation, the formal theory of computation. It is about finiteness, and by that sense, in that extension, of discreteness. This is where computation comes in. Now, computation at a fundamental level. So all the things we are talking about, nature being constructivist and what are the building blocks. And when I say theory of computation, what I mean is the Turing model. Alan Turing's model is a model of universal computation, in a sense. Every computer language and even formal language can be simulated on a Turing machine. Of course, you can have things that go beyond the typical computable problems, and then you get into the realm of oracles and hypercomputation and those things. So the main thing about computation is finiteness, what we otherwise may interpret as physicists as discreteness. And one may ask, just for interest, so what is such a theory of the infinite? Mathematics has infinite. There are all kinds of transfinite math and algebras, etc. One may ask, what is within computation? Then there are all these important insights about Gödel and others who spoke about incompleteness and so on, which again relate very deeply to the basic theory of computation. And one may ask that for things that are non-computable or irreducible computationally, one should ask, what kind of theory of infinities is there? Now, within math, infinite is not one thing. There are towers of infinities. And this tower of infinity is again an object of study. But for physical purposes, for the kind of physical theories we want to construct, because of our motivations of being finite and so on, we are automatically led to some computational approach. That is why computation is necessary for the fundamental foundations of physics. For that reason, it's not just, it's not just it doesn't just come from thin air. This is the chain of thoughts of why computation is so fundamental. Of course, you may ignore computation and you may just look for some finite building blocks, and you may come up yet with another theory of everything, so-called, which one should not take theories of everything seriously. That's almost looking like a joke nowadays. But with every approach to something, there is some structure assumed and so on, and then they make these things. But if you want to look at the meta level, you have to ask, what is such a theory of processes? And computation is an amazing theory existing since 1939. So how do we use that? And not only how do we use that, but in various different forms, people are coming to that from various angles. They are not directly starting with computation. They are starting with something like maybe it should be discrete, or maybe it should be self kind of organizing or self-constructivist and so on. And they are kind of all converging towards either the notion of a formal language or the notion of some propositional calculus or so on. All these things, they are converging on some computational system as opposed to some infinite system. And that's what that's kind of, and in a way, what we do at the Wolfram Physics Project, you may have again seen the computational side, but now that you can connect all these ideas, then it may make sense why taking this computational approach. You can take another computer. I mean, there are various models of computation. Rewriting systems is just one interesting and nice models. Even within rewriting systems, there are all sorts of generalizations. Besides symbolic rewriting, you can do diagrammatic rewriting. And in many ways, hypergraph rewritings are like that. So originally, rewriting systems were just used by computer scientists for theorem proving, formal theorem proving, nothing else. And now we are saying that, well, this may actually be relevant in some specific way, which has to be kind of defined. It's not just it's not like hypergraphs are floating in the air. So in some specific way in which such a formalization may give rise to these things. So how would it? Of course, it requires more machinery. So I have to tell you what's actually behind the rewriting systems. What kind of mathematical formalism can one use? But
so I have a question.
Yes.
Yeah. So you have going away from the continuous model and moving to a discrete model. So you have like atoms of units, building blocks, right? And I mean, computation comes into the picture insofar as we're speculating that the building blocks are interacting with each other in like a finite number of ways. Is that accurate?
We are essentially saying that there are some finite number of rules of composition.
Mm-hmm.
The minute you get out of the finite and you put infinite in some ways, then you will automatically get out of kind of standard Turing computation. So we want to stick to everything finite, and that means we want to stick to everything that is algorithmic, computational, and so on. That doesn't mean that there are problems that are not computable. That's part of the thing. Those kind of incompletenesses that Gödel pointed out to are part of the they are the kind of feature rather than the bug. But in all these approaches to formalizing the foundations of physics, it seems to converge on the fact that we should have everything finite all the way along, or computable all the way along. So that's what. And when that happens, as I pointed out, that when something is computational, now in the theory of computation, there is an inherent logic that computational systems express, like the lambda calculus, which is the basis of standard computational for formal computational languages. They are expressed in intuitionistic logic. So again, computation expresses that, and these people also came to that conclusion without necessarily using any direct inspiration from computation. I'm just trying to point out that all these things are converging. Okay, so there is, of course, this. I don't want to get too kind of. I want to keep the focus on what we are after, but this thing about constructivist versus classical computation versus not, you may see some guises of this in other things also. It's not exactly the same thing, but there is a kind of, at a deeper level, the same way that we say something has to be constructivist. it's kind of analogous to some approaches in other problems where you say there has to be a Bayesian or there has to be an agentic perspective, or there has to be an epistemic perspective or a subjective perspective, as if it is that the view from the inside is extremely relevant for talking about the physics as opposed to the view from the outside. And constructivism is much in that spirit. And constructivism itself is related to computation. So you may imagine that in all these other problems that are either related to maybe even AI or the mind or even fundamental physics, this thing about the view from the inside, this constructivism, this computationalism, or rather this epistemic point of view, behind all of those, computation and constructivist or computational approaches may be fundamentally there. Those are all problems that people again have been thinking about, but we just want to point out that there are some deep ideas that run across all the open problems that we are facing. Okay, so let's in order to proceed further, we should now look a little bit at what the objects are, what the players in this game are. So first, let's talk a little bit about toposes. Toposes are categories, but first I have to obviously say what categories are. So I'm not going to give you some full-fledged definition of categories. There's a whole course that people work in category theory, and the best I can try to do in the time that we have is I can try to give you some intuition of the things of category theory that we need, and other things. Besides, I mean, once you have this intuition, you may look up further yourself, and they'll also be in 2 days. In Wednesday, Thursday, there's another speaker who's a professor from the University of New York, who's a computer scientist, philosopher, mathematician. He's also going to say a little bit more about category theory, Turing machines, randomness, and things like that. So you'll hear a bit more about it over the course. So take whatever I say now, take it as a starting point, and you'll hopefully hear more. In many ways, how do we want to think of category theory? We want to think of it as a formal theory of relations. There are various ways mathematicians think about it. The two main ingredients of a category are objects and maps or morphisms, which I call relations. So if you typically, for example, if you have, let's say, some object A and some object B, and there's some relation between that, like let's say F, you may, in ordinary analysis, you may say that, well, this is some domain and this is some codomain, this is a function, and this domain has some elements, this codomain has some elements, and the function is some mapping. The category theory approach is to say that forget about what's inside this domain and codomain. We don't care about the internal structure of these things. We just think of them as abstract objects, and we only care about the relations, which are the maps. So you totally ignore what's inside this. You think of this just as abstract objects and without anything further. And everything then depends only on the maps, which are relations. And the utility of that approach is that this way, they can be things more general than functions. These things can be entire mathematical structures. This could be a whole group or a whole mathematical theory, or this could itself be a category. And then you can have a map from a category to a category. So it's all about relations. It's a formal mathematical theory of relations. And relations will be extremely useful because even from the physics side or from the philosophy side, you may have heard about this kind of this tension between those who think that it's all about relations versus those who think, no, there are some fundamental truths about the universe, which are absolute truths. You cannot prove or disprove them, they are just there. And others say, no, there are no such things. It's all the basic things emerge from interconnectedness, from relations, and so on. So at many levels, for that kind of metaphysics, one needs to ask what kind of relationality, what kind of theory of relation should one use? And category theory is a great formalism. Of course, it was not invented to solve philosophical problems. It was invented actually to be a replacement to set theory for the foundations of math. And in a diagrammatic sense, besides this, an ordinary category satisfies a few axioms. If you have a third object C and you have a map G, then you say that the composition, actually it's written the other way around, but here I'm writing this way, that this is also a map. This is also a relation. So if you have two relations which compose like this, then the composition is also a relation within the category. It's a map that exists, as opposed to saying that you can compose, but that thing is not inside. It's like saying that you have some you have some structure, but when you combine it, the combination looks like something different from all the ingredients inside. Here it's just trying to be specific that when you make such compositions, whatever you get has to be in the category, not something outside. You don't get out of it. So if you get out of it, it's not a category, then it's something else. So one of the things is that, and then there are some other axioms which in diagrammatic form I will just draw. One of them is just saying that there's some identity map. So if there are two things and you have this, which means this map goes from the same object to itself, and then it goes to this, it is equivalent just from going from here to here. So to say, meaning that if this was A and this was B and this was the identity map and this was an F, then the composition of the identity composed with F equals to F, similar to typical identity axioms. So you have this, but the most important axiom diagrammatically of a category is associativity. So the best way to draw associativity is again by a picture. In many ways, you can simply think of a category, you can just represent it as a graph. A finite category, you can represent it as a graph. The objects are the nodes and the relations are the edges. And the type of graph you can generate gives you exactly the representation of what is so-called a small or finite category. So you have this compositionality that's ingrained, you have the identity, and the most important, you have associativity. So the best way that I like to draw associativity is something like this. Let's say you have object A, you have object B, you have object C, and you have object D. Now, if I compose AB and BC according to this, I should get a map AC which lives inside. Then if I compose CD, then this composition should give me this one that lives inside. So what I've done is I've taken this and this. So AC, let me just write it somewhere here. So I've taken AC and CD to give me DA. But I could get DA in a slightly different way. Instead of going this way, I could have actually also gone this way. Meaning that I take AB and I compose it with BD, where BD is the result of BC and CD. So if I just, for the moment, erase these dotted lines, then in order to get to AD, there are two ways I can do it. I can either get the map, the relation AD, by following this path or following this path. Associativity, as a fundamental axiom of most mathematical systems, says that when you follow these two different paths, the end result is the same. Meaning that the map that you get here is identical. Just for kind of discussion, the map that you get following the white path is shown in white and the other is shown in blue. There is no reason to assume that the white and the blue path here going from this are the same. They could well be a different relation between the same two objects. But associativity says that no, it is an identical relation. And associativity is extremely important, as you've seen in previous talks of hypergraph algebras and so on. So that's again built into the definition of a category, and you can see it this way. If you, in a way, if you like, I'm not going to go more into it, but this picture I've drawn, if you just look at this picture more carefully along with these lines that are the dotted lines, this would look like a tetrahedron, a closed tetrahedron. And if these two things are not identified, the tetrahedron will be open. So associativity is giving a picture of a closed tetrahedron. It wouldn't close if it was not associated. So anyway, so with these basic axioms, one defines a category. Of course, the whole thing about category theory is not just this definition. The thing is what you can do with this. And what's so powerful is that because this is so abstract, with this people do all kinds of things. They start defining abstractions of products and quotients, all the things that you do in mathematics typically, you can abstractly formalize it from these kind of things. And from that, some more kind of structures can be built. And then you can ask questions like, what's the relation from one category to another? What is the category of all categories, and so on? And you can really then build up all kinds of mathematical machinery. So among the kind of categories, there's one special category called just bold letter sets, which is the category of sets. What are the objects? Every set is part of that category, and the maps between sets are just ordinary functions. So that's called bold sets. That is the category of sets. Now, this one has some very special properties because it is not itself a set, mind you, obviously. It's just a category of sets. And it has certain special properties which are inherited because of the fact that all the relations are functions. And some of the interesting properties are that on this kind of thing, Cartesian products, disjoint union, singleton set, all those things are well defined. A singleton set is just one object of such a category. A Cartesian product can be abstractly defined. So in typical math, when you look at your standard Cartesian product definitions, you can actually abstractly express it in this framework. And that's why mathematicians went about kind of founding math in this. Another important object that you have is, just as you have the notion of a subset within set theory, now there's a notion of a subset. But I told you that in category theory, you only care about the object as a thing. You never look inside. So what would it mean to say that there is a subset? It would be meaningless. So you do not look at a subset in that way. What you do is instead, you just look at these maps. And if this object had some notion or some analog of a subset, it would be another object that would be related to this via certain maps. So you're looking at things in a totally, from a kind of global perspective. Instead of looking at the thing itself, you're looking at what it does, and based on that, you're inferring a definition of what in category theory people call sub-objects. But sub-objects are sub-objects. They are the analog of subsets of the objects, and they are defined without actually looking what's inside the object, just by looking at the relations. So that's a little bit interesting and amazing how it works, but those things work well. Now, not every category will have all these properties. The category of sets has these properties because they are functions as relations. So toposes are categories that behave like the category of sets. This is one instance of a topos, but toposes are all categories which have properties that are similar to that, meaning that you can have other categories which are not, whose objects are not some set and functions. They may be other things, but they still preserve some of these properties, or at least let's say these properties. So that can happen. You can always take other kind of wild categories which have nothing to do with these properties, and those are not going to be toposes. So essentially, toposes by definition are the generalization of this category of the category of sets, and they have similar properties. Now, these toposes turned out to be useful in the same way, like, when people realize that when you want to do something either in mathematics or physics, if you want to do things which are purely classical, you can work with set theory, you can do a lot of interesting things. But once you want to start going beyond the standard classical realm, you start requiring other machinery, and you need some generalization. In a way, a topos is a natural generalization of whatever properties the category of sets was giving you. And of course, you may ask that what about beyond that? You may look at other kind of categories, but it turns out that there was a lot of interesting physics just to be discovered in toposes. And that is what Isham and his collaborator did. One of the interesting properties that turned out is that when you look at, when you look at set theory, since the objects are sets, you can have various compositions like union, like union, intersection, and so on. You can start, which have to be defined in some kind of products and so on. You have a natural logic expression of some logic internal to such a category, and that is just Boolean algebra. When you work with toposes, what happens is that the sub-objects of a topos give you a natural generalization of Boolean algebra in terms of what is called the Heyting algebra. I'll tell you later what the Heyting algebra is. But for now, for the Boolean algebra, you may just think about this as there are many ways to define a Boolean algebra. It's usually thought of in terms of given a set A, you have some logical primitives like meet, join, or you may think of it as the and or operation, and there are a bunch of axioms that it has to satisfy, which you may have seen in various kind of math courses, and that's typically what people would just call like classical logic and so on. And so such a category in its internal structure, which expresses Boolean algebra, generalizing it to toposes gives you a generalization of Boolean algebra. Now, this generalization can be again formalized in many ways, but there is one simple thing in which this Heyting algebra turns out to be useful, and that's the following: that when you are working with your classical logic, you have, and if you take a proposition, let's say alpha, if you say alpha and you say or negation alpha, that will always be true, right? Like, or either this or this. Nothing else can happen. This generalization basically says that this does not have to happen, meaning that instead of being equal to 1, sometimes they say this is less than 1. And what that means is that a proposition in such a Heyting algebra or in such a topos can neither be true nor false. Now, you may say, what does that mean? But you've actually seen such cases of things that are neither true or false. And that's, again, nothing but our good old theory of computation. You have problems that are undecidable. You can look at those problems like the halting problem or so many other problems in the theory of computation. At the end of the day, you're not going to get an answer true, false. It's undecidable. And that's what's being captured by intuitionistic logic. And intuitionistic logic is exactly what is coming in Heyting algebras and in these toposes. So again, a natural convergence to this idea that computation already has. Of course, you may think that, okay, well, I mean, if these are deep connections, maybe we should just kind of express a theory of computation in terms of these things. You may do that. And when people have thought about such things. But I'm just showing you all these different roads that all seem to lead to Rome, so to say. And I'll say a little bit more about this. Another implication of this thing that I wrote, which is also part of intuitionistic logic, is that this notion of double negation being the identity. So, you're used to our common sense thing that if I negate something twice, I should just get back that. That's classical logic. You would have to give that up if you want to search for something deeper. And in the world of computation, one does have to give that up. Because if this is not true, then this cannot hold. Meaning that even if you double negate, it's not going to be back to itself because it's not true or false. There's something between true and false. In some courses, you may have heard of this thing as called the law of the excluded middle. In classical logic, you have the law of the excluded middle. The middle is excluded. It's true or false. But when you don't have such an axiom in your logical system, then you have something that could be neither true nor false, but undecidable. So the thing about logic is not something set. Logic is like it's like a game of Lego. Depending on what axioms you put in, you'll get some formal system. That formal system may express something, that what it expresses may be finite, maybe in certain cases transfinite, and so on. What we are interested in is in those kind of logical systems that seem to be inherently kind of tied to our notions of discreteness, finiteness, computation, and so on. And all these things are coming together. So that is why toposes are interesting. In many ways, the word topos means place in Greek. And a topos is the formal place where foundations of math can be done. So if you want to say, upon what basis should math be built, the topos is your point. Like in the past, you said a set was the thing. You take a set, or you take the set of sets, or you take a category. So mathematicians are now saying a topos is the place to actually build all of mathematics, and that's what they're trying to do. And in this approach that Isham followed, they came to this in their own way. Now, as I said,
can I ask you a question? Can you say, have we encountered Are we likely to have encountered toposes in our daily life at this point? Or is this just gonna be a new abstraction that we're just gonna have to work to understand here?
And what do you mean by have we encountered a topos?
Well, so you said there are these things called toposes. Okay, I don't know what they are exactly.
So, but
Have
I
I
think-
encountered one before?
If I ask you, have you encountered a category? What's your answer to that?
I guess I would say yes, now that I kind of know what it is.
Okay.
Yeah,
so-
but I don't know what a topos is.
But toposes are just categories. They are categories.
Uh-huh.
They are a special class of categories that have the same properties as the category of sets.
They have the same properties.
But they are categories. They are not other than categories. There are all kinds of categories one may conceive of. These are a special class of categories. Because of some properties or because of some axioms in there, you can do interesting math with it.
Okay, and so follow, just to be clear, are sets like, is the category of sets fall under is it a topos?
Yes,
Well,
yes. It's a
okay.
special topos.
It's a special topos. And would there be other toposes that we might have seen before other than sets?
You may not have seen, depends on or depends on the class you go to, but yes, you won't see it in a typical physics class. That's true.
Instead of like sets, you could have like graphs. Like
So here are some examples. You can just have a look at the last slide. So one is just a category of finite graphs. Another is what is called a category of G sets, a category of presheaves. I don't want to say about what presheaves are, but I think as John was saying, this is the other next simplest example. Just a
Okay,
category of finite graphs.
okay, I see. With the morphisms being transformations between graphs, or
There are many ways you could think of them, but essentially they are maps between graphs. Those maps can be you may specify them in various ways. One of them could be just transformations. It could be permutations. There are many ways you could do that.
I see. Okay, that's helpful. Thank you.
Yes.
So I understand the category of sets, things which behave like sets, right? Now, what is a topos? Is it a category of sets or an example of a category of sets?
It is generalizing the notion of a category of sets, where the category of sets is a special topos, and other categories whose objects are not sets but other things, and they have similar properties to the category of sets, those become toposes.
So topos behaves like set theory.
Don't say set theory, say category of sets, like the category theory of sets, not set theory itself. Because as I said, in category theory, you never look inside the object. You never look inside the set. You don't care about what the elements are. You just care about the relations. It's not set theory because you're not actually looking inside the set. In all these cases, that's the whole point of relationalism.
I understand category of sets. That means we're not looking into sets. We are looking at objects and morphisms.
Yes.
Such that objects and the morphisms, they satisfy the set like
Some set-like properties.
properties.
Yeah.
So
So you're making a collection of all the kinds of categories that have set-like properties.
the category itself is an abstraction, right?
Yes.
Isn't that enough for us?
No, it's not, because they may be very wild type of categories which have nothing like the properties you want, and then they may not be interesting. So after all, set theory is not some garbage to just be thrashed away. Despite its problems, there are some useful properties in set theory that help people to build various.
I understand. Based on the definition of a category, we're interested only in the
Special type of categories.
the closure, the identity, and the associativity, right? So if we have those abstractions at that level, then we're no longer looking into sets, right?
Yes.
The category is an abstraction.
Yes.
So I'm still trying to understand.
No. So what happens is that in this, no one has told you what is the nature of these relations. So you're just saying that, well, these are relations, but these relations can be further specified. And depending on the type of category you look at, these relations will have special features, will have special
So
properties.
we're talking about different categories, right?
Yes,
Um,
it's not one thing.
I can understand a category as an abstraction,
Mhm.
a category of sets. But are we talking about category of categories?
You could even talk about that. That's the point. There are many types of categories. That's the whole.
So can you give an example of one category which behaves like set? The category, a category. Can you give an example of
Yeah.
two categories of sets
You can just take.
which behave like the?
You can take these, any of these.
What is?
There's only one
finite
category
graph?
of
What is
sets.
the G set?
Forget about the G set. Let's just take a simple case. If you take the category of finite graphs, where the objects are graphs, and the morphisms are just transformations between them. It also has set-like properties. And these are not sets, these are graphs.
Okay.
So the thing about category theory is, it's not about one category. It's a framework for constructing all kinds of categories, because they may be useful for abstracting all kinds of objects in math. In fact, all of math, that is the goal. But among all the various wild kind of categories you can write, certain important properties are useful to do the kind of math that people care about. And that's why they narrowed down on this subclass, which happens to be toposes.
Okay.
Yes.
Thank you.
Okay, now maybe I've just been thinking about this all wrong the whole time, but the way I generally conceptualize a topos is literally just, all right, suppose you have boxes and everything, you have your set here, the chairs, blah, blah, blah. Literally just draw a bubble around it and just see the relationship-based connection that it would extend to. Now, as Xerxes was saying, there might be multiple relations, but some things may hold relations via one topos, but not the other. They may share that with others. Is that kind of?
Yeah, the other thing you wouldn't call a topos.
Okay, sorry.
So I mean, in a way, why this is not enough is because even if you say that this is some abstract theory of relations, you do care about what kind of relations we need. Relations also can have further specifications. And those specifications may be in terms of certain properties that this system of relations may have. You have a system of relations. Think of it as a formal system, like any system. It may have certain features based on the kind of relationality it is expressing. Different systems of relations may express different logics, for example, may express different properties. So you may use it for different things. As you know, if you take one logic versus another logic, it's not going to express the same let's say, system of algorithms or processes that you want to work on. So in a way, these relations are expressing different logics or different properties. They will be expressing different mathematical constructions. So now we even want to narrow down into what type of relations we want to talk about. Yes.
This is maybe a tangential question, but you notice, or you mentioned, I think more than once, that we can speak rigorously about a category of categories, right? What is it about a category theory that prevents something similar to a Russell paradox happening? Like how does the way we set up category theory allow us to talk about a category of categories, which is different from set theory, where we can't speak about it as a set of all sets?
Yes, because one of the things is that when you speak about, okay, there are more than one answers for that. When you speak about the set of all sets, you are trying to explain it from certain axioms of the same type of thing. It's still a set. That set of all sets is still a set, have to satisfy the same axioms. But when you have a category of categories, that will start having different properties organized hierarchically.
No, but we have not talked about categories of all categories, right?
Not yet. We don't need that.
I think Gary was mentioning.
Yes, we won't need that. But what we'll actually talk about will be, instead of set theory, we will talk about type theory. Type theory, again, is something that is used in like traditional computer science. It is the kind of cousin of set theory. It gets rid of this problem simply by giving a specification to what a set means. The word type comes directly from the word data type. It means that you can't just take a set and say, this is a set, that is a set. You have to give it a property. You have to say, this is a type of a set, that's a type of a set. If this is of this type and that is of this type, you can't just throw objects from one to the other. Membership is not freely exchangeable like that. So set theory solves it by that, by making a further specification. The problem with traditional set theory or the Russell paradox is because of the circularity. To break the circularity, you have to put some further specification so that you are not talking about the same thing itself, not reflecting back to the same thing. When you do that, it's a different object. And category theory also allows you, because of the hierarchy of categories that you can build and the various kind of things, it allows you to get rid of that self-reflexivity. Again, category theory by itself is not, so even in set theory, like when you say set theory, it's not just set theory. Set theory is actually what is called the ZFC, axioms. So there's axiomatization of set theory. And then within that axiomatization, you do arithmetic and so on. In category theory, you can't just work with categories by themselves. You also have to actually specify and make some axiomatization. And often that is done in type theory. But by itself, category theory is a very loose kind of thing. To do something, you have to actually put some more axioms, you have to put some rules, and you have to take care that all these self-reflective things are not there. And you can do that by making further specification. It's simply the thing, like if you have less information, you may run into this thing that two things get identified. But if you have a little more structure, you may be able to dissociate them by putting little more features. That's the kind of short answer. Okay, so well, essentially for computation, I told you what the motivations are and where it comes from. So let me just quickly summarize what these people, what Isham and Doring were doing. They stumbled upon these toposes, and what they said is that in every topos, you have these two objects. One is called the state object, and one is called the value object. And physical observables are maps from state objects to value objects. So in a way, they started then kind of building up formalism, so expressing classical mechanics, quantum mechanics, etc. within a topos. So you have to say this is like the analog of a phase space, this is the analog of a value space, and then physical various observables are maps. And in this approach, as I mentioned, the law of the excluded middle doesn't hold. So this is what I already mentioned, that in intuitionistic logic, you have this identity holding. In classical logic, you would have this. And in these toposes, except for the category of set itself, in general toposes, you will have a generalization of Boolean algebra, and that will lead to these kind of things. So at this level, this seems quite abstract. But what they could do in all this is that they could say that, well, the kind of systems that essentially the framework isn't about equations of motions. At best, what they are doing in all this formalism is that they are expressing physical observables as certain maps, and then they are trying to use the inherent logic that is within this framework of the topos and combine observables as logical operations. So they are literally thinking of observables as logical propositions and combining propositions with logical operators to talk about when two observables co-occur, what is the result. So all those things that you may physically think of as kinematics. Kinematics is expressed via the underlying logic of this framework. A proposition is a proposition about a system, such as the observable taking values, is simply expressed as some map between the state object to some value object. And since the logic only allows you certain ways of expressing, this inherently gives you things that you may otherwise relate to computational things. So the take-home message is that within this, you can talk about kinematical assertions of observables using logical operators. So now it's like very base level framework. You're literally using the underlying logic. We're not talking about things at a higher level. But there's only kinematics, mind you. There's no dynamics in this system. Where will the dynamics come from? That's where our rewriting systems will help. Our rewriting systems will add something more to these structures, and that's where the dynamics will come. So we'll go to that. Okay, so essentially, I'll just give you two examples and end with this kind of thing. What they identify is that if you just work with this bold sets, then you can actually express within this framework, you can actually express classical observables in classical physics or classical mechanics. And if you want to express quantum theory, they came up with this so-called category of presheaves. At this moment, you don't have to worry about what a presheave is, but essentially, they started looking at a category of bounded operators on Hilbert spaces. And within that, they were able to express kinematics of standard quantum theory. This is not the only approach. More recently, if you look at certain talks related to quantum computing, where people use these diagrammatic expressions of the ZX calculus related to the Z and the X operators, that is yet another category theoretic approach to quantum processes. It is not a complete quantum mechanics because there's no dynamics, it's only kinematics, but it's an approach to quantum processes. So when you say kinematics, all these approaches to process theories can be expressed in this categorical framework. So there are more than one ways to do that. And this kind of thing gives you a general framework. So the natural question for us is that, okay, all this is good. How can we push this further and start talking about not only kinematics, but also dynamics, and maybe connect it more closely to computation? Because all these things really smell like there's computation going on. But the way these people approached it, they weren't thinking of computation as the starting point. They just had other kind of motivations. But all this is now coming together. So let's introduce ourselves to a few more actors in the game. And so the next thing is, what's a formal language? Now, in the previous work, what you saw is that once you have a topos, I said that it expresses some inherent logic. But what it really expresses is some formal system, and that formal system is actually a formal language. In a way, a logic is not just a logic. A logic is usually expressed within a formal language. And formal languages are the kind of analog of what the Turing machine would be to computation. Formal languages are to all languages. Or in this case, we are interested in all computational languages. So a formal language will have some grammar. It could be the Chomsky grammar, or it could be some other grammar, and it will have some inference rules. And even natural language, you may say, can be formalized or abstracted via these formal languages. So what is a formal language? How do we define it? So in the most general way, a formal language simply refers to a collection of well-formed strings. These strings can be an alphabet with some finitely many primitives. And the well-formed part refers to some generative grammar. So essentially, here I'm not talking about semantics. I'm just talking about syntax for the moment. So you have some primitives. You have a grammar which gives you the rules of composition, and you can form the words of the language. And this could be very simple. So for instance, if your primitives are A and B, and your composition rule is that A can compose with B, then the words that you can get is like AB, AB, or something. You can just go, depending on what you're allowed to compose, you can keep composing and build more and more complex words, so to say. Those things are just words of a language. So, but that would be by itself not very interesting language. We need a little bit more. So for theorem proving purposes, one may want to equip a language with something more than simply words that are allowable words that you may have. So beyond the allowable words, you typically put some extra axioms, which sometimes people call proof systems. Now, these are axioms. They are axioms or inference rules, which tell you that when you have certain compositions of words or certain compositions of words with various primitives, what do they imply, or what can they infer? So this is like really setting up everything that you see in typical logic. In fact, you should not think of logic as logic itself. You should think of it as a formal system. So these proof systems are telling you what kind of inferences can you use. And proof system is the start of trying to think of algorithms and theorems and all that. And for us, a formal language equipped with such a deductive system is what we call a computational language. Because for the type of proofs that we care about, we care actually about proofs that are algorithmic or computational. We are not interested in so-called proofs which may not be computational or which may involve something infinite and so on. So we are interested in proofs in the traditional in computational paradigm, and that's what we call a computational language. And what's interesting is that in such a language, it doesn't have to be dry and boring. It's not like this just has to be A, B, C, D, and something. These strings or these letters of the alphabet, they don't just have to be symbols. they could be graphs, hypergraphs, operators, diagrams, they could be anything. They could be as general as you want. And that will, in fact, that is what people do for more and more interesting things. There are all these in quantum computing, you have all these diagrammatic calculi where you have these Z operators and X operators. And so just writing them in terms of some equations, you express them in some diagrammatic calculi, and you have diagrammatic rules of composition. And this could be in like higher dimensions, 3 dimensions, and so on. So all those are languages. You can even just take graphs and hypergraphs, and the graph and hypergraph rewriting that we are doing, it's really, of course, once you specify all the extra axioms, inference rules, and everything, it's really a formal language out there. All the stuff you've been seeing so far, once you carefully look at it and kind of constrain, it's nothing but a formal language. That's at the base of it. You can give it whatever name you want, but that's what it is. Assuming that we are just talking about computational systems at least. So what we are driving towards is that all the stuff you've been seeing so far are formal languages. These formal languages are expressible in these topoi, in these toposes, and these things naturally have they naturally express certain operations you can do at a very base level. And then the question is that in all this, how do we try to see the notion of space or time, or in this case, spatiality emerge, or geometry? We still have to get to that point, but I'm just building up the machinery so far. Okay, so this is just an example of a generative grammar of any formal language, but that itself doesn't matter so much. Now, for looking at formal languages, we need to go a little deeper. Again, formal languages, like categories, there was a definition, but the definition itself is not just going to give you everything. You still need a specific framework for building various formal languages that may be of relevance to us. So what is such a framework? Type theory turns out to be such a framework for building formal languages. Now you'll quickly see in a few slides that when I say formal languages, in what sense it's kind of related to computation, or how proofs and programs relate to each other. But type theory, again, is a framework that you may just use for maybe producing algorithms, but you may alternatively just view type theory as a framework for constructing various formal languages. Now, what is a type? So unlike ZFC set theory, where a set is an undifferentiated collection of things with some notion of membership, which can be hypothesized, proven, or unproven, the thing about a type is that a type to which an element belongs is part of its nature. So a type is like a set, which may or may not have elements, but it's not just an undifferentiated set. It has some property. And any element that that type can have has to be of satisfying that property. For example, if you have a type of rational numbers, its members, its elements can only be rational numbers. You can't just throw in an irrational number. You can't. That's the point. It's a data type. And that means that what is inside is not something that you prove or disprove. It's part of its property. On the other hand, if you say that, look, I have a type of rational number. Let's say I have a type of integers, and I have a type of well, let's say pure fractions or something. They are two different types, so you cannot put elements one into the other. But what if I want to combine them in some way? But then that's not going to be a type of numbers, integers, nor a type of fraction. It's going to be another type, and in this case, it may just be a type of numbers more generally or something. So there are operations that you can do with types, but when you do that, it's another type altogether. Its identity is different. A type has its identity. When you do things on types, it becomes a new type. So what you can do is you can make different operations between types, like you can have a map from one type to another type, and that's itself another type. You see, like that's the point. If you have a type and another type, and you have a map between another type, that's itself another type. And the elements of that type can only be maps between the first type and the other type, nothing else. It has to be that specific. Now with set theory, without making all this specification, you may not be able to do that much, and you may run into all kinds of things. And that's why in set theory, you can just take out elements, throw in elements, you can do whatever, you're allowed. It's not a bad thing to do that, but you're allowed because the axioms of set theory don't say anything more. Whereas with type theory, that's part of the definition. So in a way, type theory gives you these encoding properties of what can, and because of this encoding property, when you want to prove a theorem in type theory, you simply have to show that that type has an element. If that type has an element, that means there is an element that satisfies that property. So if you want to prove a theorem that something satisfies some relation, you simply have to prove that the type relating to that relation has a member, which means you have to find a member and your proof is done. So it's a different way of proving, as opposed to assuming that if this case doesn't hold, that case doesn't hold, then the last one must hold. You can't do that because you don't have true or false. You can have neither true nor false. So in type theory, you have to actually build the thing, which is exactly what we do in computation. The algorithm has to find the thing. If you don't find it, you cannot decide that the problem is solved or not. So in that sense, type theory is very closely related to programming languages, and it is a formal system of inference rules that combine to form proofs of mathematical statements. In many ways, you can think of this as a kind of meta system. So okay, so let's go a little bit more into type theory to see how we do compositions, etc. So there are 4 main rules of typing, so to say. One is that you declare new types, you introduce the terms that those types can have, then you use elimination rules to specify how to use those terms within those types, and then finally you have computational rules which relate the introduction and elimination. In many ways, what you do with your rewriting systems, which is what I want to argue, they're all our multi-way systems and so on. Towards the end of this talk, I will give you a complete type theoretic write-up of the multi-way system. You can not look at the multi-way system, you cannot look at anything, and I'll just give you the type theoretic rules, and I'll tell you that's the multi-way system. Because it is, at the end of it, it's a formal system, a formal language. In the formal language, I can express it that way as well. And the computational rules will be the rules you typically use in your rewriting. So all these things that we call these rules of the automata of the rewriting, those are just computational rules within some type theory. So formally, how are things written? This is the notation when you want to declare that let there be, like when you write a program, you declare certain terms, let there be something. Now go back to your programming classes. You know, when you sit in like the first programming algorithmic class, or in whichever language, doesn't matter which language, you notice that they tell you to express the lines of your algorithm in some way. Suppose you're learning C++ or C or something. You first declare things, then after declaring, you try to express what should be in there, then you express what kind of combinations can be formed, what kind of computations. And why do you do that? You do that because you want to automate that process. You don't want to tell the computer in between, no, not this, that. You want to automate it. And that theory of automation is what type theory is telling you. And underneath every programming language, there is this. So you declare a type, then you declare, this is the notation for saying that let there be a type. Let there be an element small a, which is a member of this type A. Then you can even have types that depend on other types. And like this, you can have all types of types. That was missaid, but that's true. You can actually have all types of types. And then as an example, what this means is that all the notions of operations of math you've been thinking about traditionally, I'll give you an example of a function here, but it could be for anything else, products, functions, so on. You have to break them down in such a way like a computer would know what it means. So if someone asks you what's a function, you'll say, yes, well, take a domain, it has some elements, take a codomain, make a relation, write some equation. But how will the computer understand that? Even if you're talking about a general function, a function is a type. I told you if you have a type of some objects A, type of some objects B, and you have a map that's a function type. How do you actually tell a function type to a computer that will understand that? Of course, programming languages are based on lambda calculus, so you'd use the rules of lambda calculus. So how does one do it? I'm not telling you, you have to, there are some more details, but essentially what you do is, type theory is an inference system. You first, the top line and the bottom line is to be read in the following way. You declare a type A, you declare a type B, and given that, you can then have then you're able to declare a type which is a map from A to B. So you first declare just a map from A to B. A map from A to B isn't a function, mind you. That is in our head that we are interpreting it. We interpret things in how we understand too fast. But for a computer to know it, you have to break it to its bare bones. So just by making a type that is mapping A to B, it doesn't automatically become a function. You have to then say that let this particular type take in variables. This is just the lambda expression for taking variables, where x is the variable. So let this type be something that depends on variables that itself belong to the type A. That again is not yet a function. It's just saying that it's a type that has variables that happen to belong to this. Then you have to say that when you have some element in this type, let there be some A which belongs to this, because you already said that there are variables, that should then be an element in B. Again, it's not obvious. The computer has to know it, not you. Then you have to say that, well, whatever stuff was in B, it itself is a variable that depends on A, meaning that B knows that it's getting something from A. You have to, and then you have to make that specification. And finally, you have to say that tying up all together, whatever the F was, and with all these, it itself is a variable that goes through all the elements of A and B. So everything you have to break it down. And similar for the plus operation, adding two numbers. If you have to think about it in your own interpretation, you just say, well, I mean, what's there to say about plus? Just take 1 plus 1 is 2. But as you know, in the Principia, there are hundreds of pages of just that. Not that here you have to write hundreds of pages, but these operations have to be broken down in a way that can be automated. So you really have to break it down in a very abstract sense, and type theory gives you the tools to do that. And you may also know that when you use lambda calculus, most of the time, you don't just use lambda calculus. It's not just a thing by itself. Actually, if you look more carefully, there are various types of lambda calculus. One of them is called the simply typed lambda calculus or typed lambda calculus. So often you use a typed version of it. It's not just a calculus, there's a typed version, and that typing is important. And that's what expresses all the interesting kind of things. So this is how, with type theory, you can build all kinds of mathematical structures. You can build notions of products, co-products, operations. You can build all kinds of structures, and that's what people do at the level foundations of math. Now, what is interesting for us is that with all this going on in the background, people quickly realize that there seems to be something there seems to be some kind of correspondence or duality or whatever you may call between formal proofs and programs. And that is what was, I mean, if depending on what type of classes you listen to, there is this Curry-Howard correspondence, which is now rather, it's nothing new or something, it's kind of classic computer science. The Curry-Howard correspondence, and there's a third Lambeck version, but for the moment, forget the Lambeck version. The Curry-Howard correspondence basically relates logical propositions to types. What it says is that all propositions are types, not necessarily the other way around. All types don't have to be propositions, but all logical propositions are types. Again, not all logical propositions in any kind of logic, in intuitionistic logic. If you work with intuitionistic logic, all propositions are types. And because intuitionistic logic basically expresses everything that the theory of computation can do, and type theory is expressing formal proofs because it's a proof system, remember? So that gives you a nice relation between proofs and programs. Programs coming from computation, proofs coming from formal systems. So logic and computation are closely tied. Mathematical proofs, which are logical inference systems, and algorithms, which are computational systems, have a one-to-one correspondence in the framework of intuitionistic logic, not generally otherwise. In general, they may not necessarily match. So this deep correspondence between logic and computation is the reason why lambda calculus and intuitionistic logic match up. And for that same reason, when people think about generalizations like quantum calculus, they are analogous quantum logics. And when one goes more generally to type theory, there are various categorical logics. And people also realize that all of these things you can express in category theory. And in fact, lambda calculus has been expressed within the framework of Cartesian categories. And for those of you who have looked into, for example, if you recall the talk of Nick on the quantum framework, and you saw all these nice diagrams and operations, of course, there the category part was not mentioned, but if you look more carefully into the literature, all these quantum processes, quantum operations, all the diagrammatic calculi, they are part of monoidal categories. The monoidal category is a category with a special operation called the monoidal or the tensor product. It's just, it is abstractly defined in a particular way, as opposed to the Cartesian product. And this difference between being Cartesian or being tensorial is the whole difference between lambda calculus and quantum calculus, or classical computation versus quantum computation. And then, of course, with toposes, you start generalizing the kind of logic, you start generalizing the kind of formal languages that you may be able to express. So there is this deep connection. And in fact, mathematicians stretched it even further. They said, okay, fine. You have, on one hand, you have type theory, on the other hand, you have logic, you have set theory. But what about this? This is not just enough. It even seems to have a topological interpretation. So now topology comes into the picture. And how does that happen? So if you have a set A, I told you the kind of cousin of that set, it was the type A, right? But a type is not a set, of course. But instead of using a type, instead of using a set, you have a type A. And within the framework of the computational setup that we are in, this type would, a logical proposition would correspond to a type. So types match up to these propositions. They are the analogs of that. And in topology, a proposition is represented by a space, a topological space. And a type or a set is just a space. Now, what that means is that if you take an element in a type, which is an element in a set, it happens to be a point in the space. And I told you that an element in a type corresponds to a proof of the fact that that property of that type holds. So topologically, a point in the space is a mathematical proof of some property that this type is expressing. And then similarly, if I have a kind of logical operative like the AND would correspond in set theory to just a set of Cartesian pairs. It would be some kind of direct product of types. And here it would be a product space. So everything that you are doing with a set or with a type, all these unions, intersections, operations, etc. Now you can do that with topological spaces. You can have co-product spaces for implication, a logical implication, which corresponds to a set of functions and which corresponds to a type, which is a function type. The topological analog is a function space. So, and so on. You can have fibration sections and so on. An interesting one here is a proof of equality. In set theory, when you want to prove two things are equal, or in type theory, when you want to prove two things are equal, that proof of equality, that means within a type, if you have two elements, if you want to prove that they are identical, in the topological interpretation, it corresponds, the existence of the proof corresponds to a path that exists from X to Y between the 2 points. If that path exists, that path is a proof. So spaces are types and possible paths are proofs. Now you may say, but well, I can always draw a path. No, of course not. Depends on the topological space. What if the topological space has some strange genus where there's a big hole in the middle, like a torus or something? Then there are only certain paths you can have and certain paths you can't have, which means certain proofs that you can have and certain proofs that you cannot have. So depending on the types that you're working with, you're getting a very clean mapping to some kind of topological space. And then you can just look at that topology, and based on that, you can say what kind of things are provable, what kind of things are not provable. And this was work by Vladimir Vovotsky, who died a few years ago. He was here in Princeton for many years. He was working on this thing about type theory. So this thing, what I call topology, actually is within the sub-branch of homotopy theory. In the following lectures, in the following slides that will probably come next time, I will actually tell you what homotopy is. I'll kind of give you some idea of what homotopy is, how it's constructed. So in a sense, homotopy is the topological study of paths and paths between paths, which means higher order paths. And what people came up is with all this duality, they realized that what we are actually after is not just type theory, it's what is called homotopy type theory. And in homotopy type theory, you can actually take type theory to a whole new level. And what is this new level? The new level is the following, that if you have a topological space, you can say, well, there's a path between 2 points A, B. There's another path between 2 points A, B. These two paths are different. They are not the same. They're not identical. If they are not identical, then there has to be a path between that first path to the second path, which would be a higher dimensional path. And if there are more than such paths, then there has to be paths between those paths, which should be higher dimensions. Now, of course, that how many dimensions you may have or so on, and all those things depend a lot on the details of the space. But homotopy theory takes care of all that. But what it means is that in type theory, you don't just have proofs, but you have proofs between proofs, meaning that you have mathematical statement that may have two unequivalent proofs. They are both proving the same thing, but you cannot just map one proof to another, because sitting in such a topological arrangement of that space that you cannot just translate all line by line. It's a different inequivalent proof, and then you can have proofs between proofs, and so on. And what that means is that in this thing, you can start now building a whole hierarchy, a recursive hierarchy of. In other words, this language that you are finally going to get can express all kinds of recursions up to infinity, in fact. And then this also means that we are no more, because these paths, as I said, these paths would somehow look like the relations or the morphisms. But now if I start using these ideas and start talking about paths between paths, then I'm going beyond standard category theory. These are not going to be paths anymore, but they have to be some generalizations of these paths, which means I have to start asking about morphisms between morphisms and so on. So that means I need more than category theory, and that is what is called higher category theory. Those again are things that at least the things we need about that I'll define. And so people have built these higher structures in mathematics, and these higher structures express more and more powerful formal languages. And those things, up to some limit, will on one hand give us certain limits of what you may call the limits of multi-way systems. I'm not using the word Roolead, but I'll give you a notion of what could be the mathematical infinity that may come closest to what is otherwise vaguely spoken about as the Roolead in general terms. And on the other hand, I want to tell you what it means to get the continuum out of such formal computational systems. And for that, you need all this machinery. So now let me see. I'll just end with this slide, because that would be a good stopping point. To summarize, this deep connection between proofs, programs, and physics goes in the following way. Systems of axioms in proof theory correspond to inputs in a program or in an algorithm, initial states in physics. Rules of inference correspond to computational rules in an algorithm, correspond to laws of evolution in physics. The process of theorem proving corresponds to the execution of computation in an algorithm, proofs and programs, corresponds to dynamics in physics. The theorem, the output, is the final state. It's as if I'm saying that physics is the instantiation of computation. But that's what Wheeler wanted. He wanted nature to construct herself. And what better to do such a process than a computational process? In other words, what I'm saying is that physics is language theoretic. And through the lens of constructivist mathematics, physics is indeed an instantiation of abstract computation. That's one thing, but what can we do with this? The things we'll do with this in the next, in the part 2, which actually comes on Friday, is that we will start seeing, as we saw, in all this, we could talk about kinematics, but here you start seeing how dynamics may come in. And this dynamics will have something to do with the computational rewriting rules that you see. So we try to argue how dynamics comes into the system. And once we have kinematics and dynamics, then we are good. We can actually construct some interesting physical systems. Well, in this case, it's not like I'm going to construct all of physics, but in this talk, we will focus on how we can get a notion of topological or geometric spaces. And not just how we can get, how mathematicians think about spaces fundamentally. And that same kind of thinking seems to be also relevant for building such structures, spatial structures in physics. And then those will be the building blocks of any theory or any approach to quantum gravity that one may use. This is the machine code of quantum gravity, or this could be one way to express the machine code of quantum gravity. And we also actually see some examples of some of the existing approaches to quantum gravity and how this may be expressible. So let's end with that. If there are questions, I'm happy to take, but otherwise, you don't need to be locked in here.
Thank you.
Can I ask, this point about the like discreteness of computation, I don't think I really appreciated. I mean, you start talking about homotopy theory and whatever, and I'm thinking about continuous spaces just as well as you could imagine continuous spaces in physics. What is necessary about, or rather, maybe I'll put it this way: why can't you think of computation in this kind of continuous? Not that I'm like anti. Like discretizing things.
Yes, but
I'm just curious why.
But you're saying that because you're thinking of topological spaces in the way you usually do, as if there is some continuous thing floating around. It's all about continuity and so on. The way to think of topological spaces in this setup is not to think of the space itself as your starting point, but is to think of morphisms and some limits of those morphisms as being the topological space. What one traditionally does is, in a typical topology class, you say, let there be a topological space X. Now, given X, X of course it has certain properties like continuity and so on. And then depending on some specifications of the space, you may say, fine, now let's start looking at structures on this. So it's already like you've started with something that looks continuous to you, and that seems to be contradicting to may appear like, okay, why are we using all this continuity stuff? But what we are going to go after here is, do not think of a topological space in that way. We are going to think of a topological space in an opposite way, not in terms of something that there was and then you had structure, but based on certain structures, like the maps, like the morphisms, like the relations, some kind of limits of these relations lead to a topological space. And this is related to what Grothendieck was actually saying, that a topological space is just the end result of some set of relations and morphisms when you can pack enough data into that. So a topological space isn't about some continuous thing here. It's actually a data structure of packing relations or morphisms. And that's exactly what types and proofs and all those things are about.
Okay, but I guess I'm asking, why do you need, it sounded like you needed or really wanted a discrete framework
Yes.
to work with. And I guess I'm asking, why can't you think of, and maybe I missed your point, but why can't you think of, you're making this analogy between a proof, for instance, as paths in this space. And I'm asking, why can't you think of computation in a continuous manner as well? You're saying, oh, this,
okay.
Yeah.
First of all, what do we mean by computation? By computation, we mean what Turing machines do, what Turing defined as computation.
Well, if that's what you mean, then you're already done, because it's already discrete.
Yes. So I didn't start by saying the way we started is we said that, well, physicists always wanted to seek out some framework that was discrete. So then I pointed out that, well, instead of worrying about discreteness, what we actually care about is finiteness. And then what is the process theory of being finite? And computation seems to serve that purpose. So then we'll go with computation as the thing. It serves what we started off with, and then we'll try to see how far we can stretch computation. And here, that's what we are doing.
Okay, I see. It's a matter of your starting point.
Yeah.
Thank you.
So this is probably another close question, but you were talking about we don't want to deal with infinity. Is there something related to that if there's a Turing machine that like does not halt?
Well, I mean, there are people do consider notions of hypercomputation, Oracle machines, or at least some notion of hypercomputation should capture these things related to maybe what one may call as transfinite mathematics. But those
It wasn't related to this particular topic.
Yeah.
Okay.
Yeah, those are well, I mean, we are not talking about those because for constructing kind of physical structures we want, we don't need, we want to kind of keep the infinities out. You cannot really escape infinity totally. There's something very deeply fundamental about infinity itself, and it keeps coming up in some form. But we want to tame it in such a way that we may recognize it as the limit of certain processes, but not get into it itself. It's like you approach something, and this approaching that thing is that thing, but you don't want to get into it directly. So we want to keep our framework in a similar way, because once you go into, if you directly hit something singular or something infinite, then you have to start thinking about what's the other framework to resolve the singularity. That becomes other set of problems. So here, given that our starting point was that, well, we are inherently interested in some framework, in this case for space-time or for physical theories, that are motivated for all kinds of reasons in discreteness and finiteness, let's see how far we can take an existing theory of finiteness, of finite processes, and what we can make out of that. And then you'll soon realize that, of course, like all formal systems, there are certain incompletenesses or in certain things that are undecidable or not computable and so on. Many times they have to do with something where it is self-referential, or, well, if it's infinite, it's not even part of the system. You can't even finish or maybe it takes infinite time, but you cannot ever reach the end result, something like that. So those are things that we keep just outside the boundary of what we can do for the purposes of seeking some physical, what we would believe as physically observed frameworks. It is an interesting thing to ask, what would be the mathematical theory for seeking those other things? But I think we are too far from that. Okay, then let's call it a day.
Thank you, Xerxes.
Hey,
Thank you.
look. It's like the ninja. It's like.
Yeah.